first exam, which is the midterm exam, next week, Wednesday. And the question types include matchings and choices and short answer questions or problems with multiple steps. This type of both type of questions you have seen from your class activity and the problem set. So we will have very similar question type in the exam. And the exam will be open class notes and handouts. And since we are going to use Zoom Live, you are required to log in Zoom and open your webcam during exam. And there's no discussion allowed about the questions during exam. And we will provide two extra materials. One is the terms introduced so far provided, which you can use to refer, which you can refer to when you work on the, especially the matching and the choices questions. And also we will have one previous year's exam as a sample exam for you to work on. And I encourage you to work on the previous year's sample exam in groups, in small groups, so that you can discuss the questions. Okay.
I have a question.
Oh, go ahead.
Oh, what exact sections will be on the test?
It's yeah, I missed this information here. It will be lectures 1 to 9. Lecture 9 will be this Wednesday's lecture, and the labs 1 to 4, and problem set 1 to 3. Okay.
And then can we access the Canvas during the test, or should we have things printed?
Of course, you can search around, but my suggestion is, because I mean we have limited control of your side, what you are looking for. But my suggestion is that the exam time is very limited. You'd better have everything prepared ahead of time so that you don't have to browse a lot of things to find one piece of information. Does that answer your question?
Yeah, thank you.
Mm-hmm.
Okay, me too. Again, for the previous year's exam, I went to the files and found what seems to be the previous year's exam. It says it's unpublished, so I can't see it.
Yeah, sure. It's unpublished. Yeah, so we will publish two materials today. One is the terms introduced so far, so that you can, you can either prepare around those terms, or I would strongly suggest you go back to the course packet for the materials covered so far. The terms will be used during the exam for you to make easier choices and matching problem solving. And the previous year's exam will also be provided today. It will be published today.
Will there be a key for the previous year exam to make sure we're doing it right?
Actually, unfortunately, we won't provide key because we are recycling some of the questions from the previous question pool. So just to make sure that this sample exam won't be circulated in future years, that's the concern. So we won't provide a key for this sample exam. The best solution is you work in groups, and if you have questions, you can ask before the exam time. So any more questions about the exam?
I was wondering, are we allowed to use like MATLAB or other processing things to help with like Laplace transformations? As long as like maybe we show this notes, or
if the question asks you to give steps by hand, then you have to give steps by hand. Otherwise, you are encouraged to use MATLAB.
Okay.
Yeah. But I would say it's 95% or more sure that you won't need to use MATLAB during the exam. Because for some people, if you meet technical problem using MATLAB, that will be, you won't have time to make up for the time that you miss for figuring out MATLAB problems instead of just the focusing on the exam questions. Okay. Can we go on to the summary of the lecture? All right. So you have seen this closed loop block diagram many times. Here, as you can see, something different, which is we have G1, G2, G3, and HS blocks. How to say? Expressed here, and each of the blocks we can solve using some type of FT, and also we can solve the FT using the Laplace domain, and then inverse Laplace domain back to inverse Laplace transform back to the FT, so that in each of these steps we can solve them, and by using Laplace domain transform we can how to say, solve each of these blocks. Solve G1 block, G2 block, G3 block, and HS block separately. But by using Laplace domain, because we have easier mathematical calculation, we can combine them easily and before we inverse Laplace transform. And we can replace all of the closed loop process control elements, the controller, the actuator, process, and feedback element by the G1, G2, G3, and H. And then we can work on them separately. In the end, we combine into one overall transfer function like this. And next is deviation variables. We introduced this term because we want to use it to adjust the initial steady state conditions to 0. Remember, Laplace transform assume ft equals 0 at t earlier than 0. So if we have ft equals to another constant number other than 0, Laplace transform cannot be easily conducted. That's why we want to use deviation variables to first adjust the initial condition to 0. Then we can implement we implement the deviation variables prior to Laplace transform so that we can do the transform successfully. And the deviation variables are commonly used for Laplace problems, and they describe how input and output quantities change from the steady state values, and it make the initial conditions to 0. So this will be this will be the original problem to be solved and the curve to be plotted. But before we do Laplace transform, we want to adjust the initial value to be 0 here, temperature 0 at time 0, so that we can do the Laplace transform. But make sure that in the end, we want to readjust the solution after inverting from the Laplace to the time domain to account for the deviation variables, which means we need to add back that adjustment that we made before the Laplace transform. And with deviation variables, we simplify the initial conditions to be x0 equals 0 and y0 equals 0. And that simplifies the mathematics calculation in the Laplace transform. But in the end, we need to add back this adjustment. And we, in the video lectures, we included the temperature sensor example, where we have this, we assume dynamic lumped heat capacity analysis, where we assume the sensor are is at uniform temperature. And in this case, inside the tank, we have this expression, which is rho times V times Cp times dt over dt. In fact, we have seen this before in our previous lectures. And on the outflow side end, we have h times a times t minus t infinite. So by doing an equation, equating the equations, we get ha times t minus t infinite equals minus rho times Cp times V times dt over dt. And we need the initial conditions T0 to be 0, although our initial conditions will be T0 equals T0. In this case, we need to adjust this initial condition to be 0. To do this, we need to consider the steady state, which is HA times TS minus T infinite S equals 0. Also, we need to, by introducing deviation variables to this equation, we can transfer the original equation to be HAY minus HAX equals the right part, change to minus rho times Cp times V times dy dt. And here we have several replacements. First is y equals t minus ts and x equals t infinite minus t infinite s. S means steady state. And also we replace that rho times Cp times V over HA term as tau. And here you can see tau is the sensor time constant. We introduced time constant several times already. And as you can see here, in each problem, although they might have similar transfer function, their tau term might be different. In this case, this tau term is rho times Cp times V over HA. And so in fact, this is still, the sensor problem is still a typical first order response, which means we have the typical transfer function for the first order response, ys over hs equals 1 over tau s plus 1, which can also be written as just gs. Here gs, as you can see, remember when we introduce the closed loop diagram with the notations of g's and h, and this gs is one step in that closed loop control. And often we can rewrite this transfer function to be of first order response to be ys over xs equals 1 over tau divided by s plus 1 over tau. Here we divide tau on both the numerator and the denominator. And assume we have a step change input, which is xs equals a over s. And this you can find from the Laplace transform table. The step change is with the expression a over s. And after partial fraction expansion, we get ys equals a over s minus a over s plus 1 over tau. And then we can invert using the equation 3, 6, and 15 to get our final result. And here we would like to explore the first order response of a step function. We have, as previously solved, yt equals a times 1 minus e to the power t over tau. We have the x-axis as t over tau. Remember, tau is a time constant for the sensor. And we have the y-axis as yt over a. Here a is the amplitude of the step change. And we get this. And here we have several arrows to, these arrows point to t over tau equals 1, t over tau equals 2, all the way to t over tau equals 5, which means these are the yt over a values for 1 tau, 2 tau, 3 tau, all the way to 5 tau. And that's the previous slide is the graph to show the first order response with respect to step change, unit step change. We can treat it as a unit step change because our y-axis was yt over a. We can also look at it from a table like this. And here you will have some problem solving that you will use either this table or the previous plot where you will use the typical numbers for 1 tau, 2 tau, 3 tau, or 5 tau. And we also introduced several other responses in the course package, such as impulse input and sinusoidal input. And also we covered a little bit more description of different inputs in the video lectures. So now we can work in groups and learn by doing and ask questions. Please hand in one answer per person in the end.